Hello and welcome to part 4 of module 20 in our C language series. This session is going to focus on the least cost search technique. Now, you know from the last session that in terms of our case study, there are two constraints that the passenger would look to minimize. One is the number of connections and the other is the length of the route. And we have in the last session successfully used the hill climbing search technique in order to minimize the number of connections. Today, our goal will be to find a route that minimizes the number of miles, therefore shortening the length of the route. Now, of course, we're going to be using heuristics. Remember that least cost search is a heuristic search method. The thinking that will apply today is if we find the shortest connecting flight to the destination, then that would shorten the entire length of the route. In other words, the shortest connecting flight would imply that we have found a route that covers the shortest distance to the destination. So in effect, using the least cost search, we are following the path of least resistance. Now let's go ahead and write code to implement the least cost search to make a booking for the customer. For that, we need to go to code blocks and open the project, right? So file and then click open and click on the CBP file once you're in your project folder. Once your file is opened, of course, we need to be in rest of fns.c and we need to comment out the code for the hill climbing search technique. So comment out all this code and we start with the code for the least cost search technique. Remember, this is in find connect. So here we'll put a comment saying code for least cost search. And now we start with some variables int POS and minimum distance or min dist. Remember, we are looking for the shortest distance and find POS. Right, now let's initialize a variable. So POS equal to 0. Minimum distance, we'll initialize it to a value that is greater than the longest distance. And find POS equal to 0. We have a while loop while find POS is less than fPOS. Remember, we're going through the array or the database looking for the route with the minimum distance, right? So if, again, we're using strcmp flight r, and that would be find POS as the index, right? Dot from, comma, from. That's the match we're looking for. And so this will be not, let's put that in brackets, not flight r, find POS dot skip over, right? And of course we need that bracket to close the if statement. Now if we do find that match and it has skip over as 0, then we check if flight r at position indicated by find POS dot distance is less than min distance, right? So if we do find in the array, right, an element where the distance is less than min dist, then POS equal to find POS to store the index and min distance equal to flight r at position indicated by find POS dot distance. So you see now how the least cost search is the opposite of the hill climbing search, right? Now, of course, we need to increment find POS before going back into the while loop. Then out of the while loop, we check if POS, then we use memcpy, and our destination will be to anywhere. We copy flight air at position indicated by POS dot to. So we are copying that destination into to anywhere. And of course, number of characters is strlen of flight air at position indicated by POS dot 2, right, plus 1. Okay. And then flight air at position indicated by POS dot skip over is equal to 1, right? And then return flight, we have to return the distance, remember. So flight air at position indicated by POS dot distance. Okay, and that's all. Now we can build this, and then let's run it. So our origin is New York, destination is Los Angeles. And there we have the route, New York to Toronto to Los Angeles, right? And that, as you can see, is the shortest route. Again, you can play around with this program after the session. Now moving on, let's look at the solution path we found through the program. This is our origin. That's our direct routes to Chicago, Toronto, and Denver. And then, of course, the wire routes to other destinations, including those to Los Angeles. And this was our solution path. Now, it may have occurred to you that this was the same solution path we found using the breadth first search technique. But if you recall, using the breadth first search technique in our code, we did examine the route New York to Chicago before then, of course, examining New York to Toronto. The reason we are not examining the New York to Chicago route in the case of the least cost search technique is because the least cost search technique follows the path of least resistance. And if we look at the routes, New York to Chicago is 1,000 miles versus New York to Toronto, which is 800, right? And then, of course, we've got Toronto to Los Angeles, 1,800, which gives us that total of 2,600 miles, right? Which, as you know, is the shortest route. Now let's go ahead and analyze the least cost search technique. We found a good solution. We found, in fact, the shortest route to the destination. And in general, the least cost search works fairly well. The problems that we could encounter using the least cost search technique are similar to those that we would encounter using the hill climbing search technique. But remember, using the least cost search technique, we are following the path of least resistance, going downhill, if you will, versus uphill using the hill climbing search technique. And so we have false valleys instead of false peaks. We have lowlands instead of plateaus, and we have gorges instead of ridges, right? So essentially, the problems or the disadvantages are the same, but in reverse, if you will. The conclusion, therefore, is that we cannot really say that the least cost search is better than the hill climbing search technique, but it will definitely outperform blind search techniques like the depth first search technique and the breadth first search technique. As I mentioned at the beginning of the session, our goal was to shorten the length of the route, and we have indeed done that using the least cost search technique, minimizing the number of miles, right? Now let's discuss the basis on which we choose a search technique. Now we know that heuristic search methods work better than non-heuristic search methods, but of course we may not always be able to use heuristic search methods simply because we may not have enough information, for example, to qualify that a node is on the path to the goal, right? So the first question we will ask when deciding on which search technique to go with is, can we use heuristics? If the answer to that question is yes, then we can either use hill climbing or least cost, and deciding between these two would of course depend on the aspect of the problem you're looking to maximize or minimize. If heuristics cannot be used, then the best option is to go with the depth first search, unless there is some information to indicate that the breadth first search is better in that situation. Now, there may be some cases where you're seeking a near optimal solution, but you don't want to use the exhaustive search. In that case, it's best to apply all 4 search techniques, look at the results, do a comparison, and then select the search technique that is best suited to that situation. Remember, each search technique will give you different results. Sometimes, though, it's a good idea to find several solutions to the same problem. Right? We're not talking about all solutions, because all solutions would include the exhaustive search. But when we talk about several solutions, what are the advantages? Well, the advantage is that we get to see different ways to approach a solution to the problem before implementing that solution. This is similar to, for example, remodeling your home. You may want to look at different layouts, different designs before you decide on the design that is best suited for your home space, right? So that you're making the best use of the space in your home. You would also probably look at the aesthetics of the design, right? Now, there are several different methods that can be used to find multiple solutions. We're going to discuss 2 of them. One is path removal and the other is node removal. And talking about path removal versus node removal, in the case of path removal, we would remove an entire solution path from the database. So essentially, we would remove all the nodes from that path before attempting to look for an alternative solution. In terms of code, this would run within a loop, right? And path removal can be likened to pruning a tree, essentially cutting off an entire branch, if you will, from the tree. In terms of node removal, we would remove the last node in the solution path before attempting to look for an alternative solution path. Again, in terms of code, this would run within a loop, right? So now let's go ahead and write code to find multiple solution paths using the path removal method. Let's go back to code blocks, and in this file, that's rest of fns.c, we'll need to comment out the least cost search code, right? And we will uncomment the code for depth first and breadth first. So just do that first. And of course, this is in our find connect function, as you know. Now the changes need to be made in main.c. Right? What we're going to do is we'll comment out these 2 lines of code, right? So, and you can put in a comment here saying code for single solution, right? That's just for your reference. And another comment saying code for finding multiple solution or solution paths using path removal method. Again, this is for your reference. Now here we have a do while loop, and this loop will continue as long as, and we're using get here, get not equal to q for quit. Okay, since we're using get, we need to include con io.h. Right? And once we've done that, within this loop, we call is flight, just like we did for the single solution, sending in from and to, and we call route as well. Now we set the top of stack to 0. So every time this loop is executed, the backtrack stack is cleared. Remember already, if we look at this code that is in the find connect function, you can see here that we're changing skip over to 1. So for every connection that we've already checked out or examined, this is changing to 1. So it cannot be found again using this or when this find connect function executes, right? That was the objective of having that skip over field. So what will happen is, since we are clearing the backtrack stack, we will have an entirely new solution put onto that stack, right? So let's now build this code, run it, and we should see multiple solutions. So New York is our origin and Los Angeles is destination. You can see the cursor waiting there. We've got the first solution, New York to Chicago to Denver to Los Angeles. Distance is 3000. Press any key except Q. You'll get the next solution, New York to Toronto to Los Angeles. Distance is 2600. Press N again and you'll get New York to Denver to Los Angeles, which is 2900. Right? Now, if I press N again, I'll get a 0 because essentially all these connections have been marked in terms of their skip over value being changed to 1, right? So they cannot be found again using that find connect function, right? So now we quit and end the program. Yes, I hope that's clear. Of course, you can play around with this program after the session. This ends our session for today. In the next session, we'll write code to find multiple solutions using the node removal method. So till then, take care, stay safe. Bye.